So this is problem number 1 on workshop number 6. So the biggest thing when you get questions like this, you got to look at those 4 factors. What are the 4 factors? The electrophile, the nucleophile, the leaving group, and the solvent. So what I've done here, at least one of these we can just like essentially cross out. So I haven't actually shown any solvents. So that's kind of just a non-thing. Right? It's a non-starter. The electrophile here is what? So the electrophile is actually the same for all of these. And what kind of electrophile is this? What kind of electrophile do we have? It's a secondary, and it's allylic. Right? So you got to be able to identify the electrophiles. It's secondary because this carbon is bonded to 1 hydrogen. If it was bonded to 2 hydrogens, it'd be primary. If it was bonded to no hydrogens, it would be tertiary. But this is not just secondary, right? It's secondary because of that, but it's also next to a pi bond. Just a pi bond. That means it's secondary and allylic. If it was a benzene ring here, it'd be secondary and benzylic. This is secondary and allylic. So looking at the electrophile, secondary and allylic, does that eliminate any of our mechanisms? Sn2, Sn1, E1, E2. Does that eliminate anybody? Secondary allylic is possible for all of those. So that's consistent. That's actually helpful. That's consistent. Right? So that's not changing. That means I don't have to, do you have to look at that factor anymore? No, you don't have to worry about it. It's the same. So so that's kind of checked off. Is the leaving group changed in any of these? Or is the leaving group the same? It's the same. Right? So is that going to be a factor we're going to need to worry about? No, right? So again, it doesn't change. So we've essentially, in this problem, we've isolated the nucleophile as the only factor that we're going to look at. And what matters for the nucleophile in these reactions? How reactive it is and what its size is. Reactivity and size. Reactivity and size. Right, these are the 4 factors. We went through this for every single problem. For Sn1, Sn2, E1, E2, we went through these 4 things. That's right. In this case, we're isolating just the nucleophile, and we're going to look at the reactivity and size. That's the important part about it. So, what do we remember? Reactivity. So reactive things are which ones? Which type of reactions want to be reactive of these 4 down here? Reactive nucleophiles are the charged, so that's Sn2 and E2. They like the reactive nucleophiles or bases. E1 and Sn1 want the less reactive ones. Okay? Who wants the small nucleophiles? Sn1 wants a small nucleophile. What else? Sn2. So green is small. Blue was reactive. Who wants large nucleophiles or bases? E1 and E2. And of course, unreactive would be, why not throw another color in to make this as confusing as possible? That would be unreactive Sn1 and E1. So not charged. Okay, so now let's look at our possibilities. How would you describe this? Is it charged or uncharged? Charged, so is it reactive or unreactive? Okay, it's reactive, so that means it either has to be E2 or Sn2. Is it small or big? Big. Who wants big? E2. So what kind of reaction is this one going to be? E2. We'll worry about the mechanism later and how that reaction actually works. We just identify it now. Well, this next one, is this reactive or unreactive? Not charged, so it's probably unreactive. Is it big or small? So unreactive and small, what does that tell us? Sn1. Next one down. Charged, so it's going to be reactive. Is this big or small? Small and reactive, that's going to be Sn2. Last one, looks pretty big, unreactive. What's one this going to be? E1. Okay. So make it simple on yourself. Write down these 4 things as soon as you get the exam on Friday. Write down reactivity and size, we look for a nucleophile. Write down the types of electrophiles. Write down the types of leaving groups. Write down the types of solvents. You'll have it there. The answers lie within. But don't overcomplicate it, right? Isolate the factor. This is secondary allylic, that can be anything. Okay. Leaving group's the same. That can't be it. The solvent, we don't even have the solvent, so it's not even an issue. It's all, this case was all about the nucleophile. Isolate those factors and remember what's important. All right, let's take a look at one particular example, an E2 example. So we've decided this is an E2 reaction. It's secondary allylic electrophile. It's got a bulky reactive base or nucleophile. And we're going to do an E2. How many steps is an E2 reaction? 1 step, so it's concerted. We need things to be anti-periplanar. Now, it's not going to be an issue here because if we'll identify our beta hydrogens and we'll see it's not an issue. But the first thing you should do in any elimination reaction, right? In E1, once you form the carbocation, you think about rearrangements. And in E2 reaction, you need to find your beta hydrogens. Beta hydrogens. Now, not all beta hydrogens work. It's a particular type of beta hydrogens we need to find. sp3 hybridized beta hydrogens, right? Beta hydrogens on sp3 hybridized carbons. So we need to find sp3 beta hydrogens. That's a little different. So for instance, if I start drawing all the beta hydrogens, which of course are 1, 2, right? This is the alpha carbon here. Beta carbon, beta carbon. The beta hydrogens are attached to the beta carbon. So if I start drawing these in, there's a beta hydrogen, and there's 3 beta hydrogens here. This is the alpha carbon, this is the beta carbon. There's 2 types of beta carbons. There's 2 types of beta hydrogens. Now, this beta hydrogen doesn't work though for E2 elimination or an E1 elimination. Why not? Because what's the hybridization state of that carbon? This doesn't work. So this is nice. How many types of beta hydrogens do I have here? Just 1. So how many different types of products can I make? Just the 1. Right? With E2, just the 1. E1 might be a little different, but with E2, just the 1. These are the only that matter. They're all the same. And we don't need to worry about things being anti-periplanar because there's 3 of these, and this bond rotates easily, right? It's a sigma bond, and it rotates. It's not in a ring. We don't need to do ring flips. We don't do anything like that. There's no stereochemistry. There's no wedges and hatches. So any one of these H's will work, right? I mean, it still has to be anti-periplanar, right? But it's not as big a deal if there's no wedges and hatches and if there's no rings constraining things. So do the anti-periplanar. So the first step, these beta hydrogens, you need to take that H, the beta hydrogen, sp3 beta hydrogen. That bond is going to break. 3 arrows. You eliminate, right, the leaving group. You form a pi bond. Balance my charge. Right, be careful to balance your charge. There's a Cl minus formed. Right, so make sure you balance your charge. And that's the only product you'll make from an E2 reaction in this case, because it only has 1 type of sp3 hybridized beta hydrogens. That's the only type only alkene product you're gonna make.